In Chapter 9, you took one sample from a population, and for either theoretical reasons or because you did a treatment or an experiment with that one sample, you were comparing that one sample mean to the population mean to see if they were different. Most research, however, is done with two or more samples, where you're interested in comparing different methods of teaching. You have method A or method B, or you're interested in determining whether a particular drug has an effect, and you have a sample of people that get the experimental drug and the other group that does not. Sometimes we call that a placebo control group. But in Chapter 10, we're trying to determine whether a one sample mean is different from another sample mean. We work with two samples, where in Chapter 9, you only were working with one sample and comparing the mean for that sample to a population mean. So let's go through the process then for doing the t-test for two independent samples. And we'll always be doing a t-test when we're dealing with two independent samples. We won't be using the z-test. So we have then two samples, and we want to know whether the mean of sample 1 is equal to or is not equal to the mean of sample 2. So again, the identifying characteristic when you're reading the problem will be two samples, two means. Each of those samples has a mean. Each of those samples has a standard deviation or a variance. And we want to know if those samples, if those means are different. Our null hypothesis would be that they're the same. Our alternative hypothesis is that they're different in some way. So as the last point, an independent measure design can be used to test for differences between two distinct populations, such as men versus women. Do women and men have different grade point averages? We might be interested in that. We get a sample of men, we get a sample of women who are taking a statistics class. We compute the mean for one, the mean for the other. Our null hypothesis would be that they're not different. Our alternative hypothesis would be that they're different. Now we could also have a one-tailed or a two-tailed hypothesis test. Women do better than men would be a one-tailed hypothesis test. Women score differently than men would be a two-tailed hypothesis test. So one of the ways to visualize this type of design is we have a population of people who could be taught, potentially could be taught with one method, and a population that could be taught by a different method, or a population that could receive one type of drug or another type of drug, or it could have to do with it doesn't have to do with people. Remember, studies can be with material, they can be with factories, they can be with any number of things, but we have two populations and two samples that we want to study that come from those populations. So we have two populations then that we don't know anything about, that we're going to take samples from, and we're going to treat these samples differently, measure the samples after the treatment, compute means, compute standard deviations, and try to determine whether they are the same or different. So bullet point number 1 is the researcher has no prior knowledge about either of the two populations being compared because they haven't been treated yet. The researcher has some idea. The researcher has some technique that he's interested in. We don't know the population means and standard deviations, and so therefore we're using t-tests. Remember in the previous chapter you learned when we do know the population standard deviations, we can use Z, but that's never the case unless you're dealing with very, very small populations. Because the population variances are not known, we're estimating them from the sample data, which is why we use the t-statistic. The purpose of doing this is we want to know whether when we treat two samples differently, or we think we're treating them differently, whether they have different scores or average scores as a result of the different treatments. Sometimes treatments have no effect, and the drug doesn't have an effect, or one teaching method really isn't different than another teaching method, or one method of producing tires doesn't produce better methods than another method, or one method of producing televisions doesn't necessarily produce better televisions than another method, or production lines in automobiles. You shouldn't be, when you do experiments like this, you have a good reason why you think one method is different from another. And in order to show that, when you have two groups, you would use the independent measures t-statistic. Sometimes we have three groups, and then we use a technique called analysis of variance. The last bullet point says, remember, if two samples are taken from the same population and are given exactly the same treatment, there will be some difference between the sample means, and this would be due to sampling error. And that's what this slide is telling you. But if you've taken two samples from a population and treated them differently, then they should be different at the end of the treatment. And we're doing the hypothesis to tell us whether that difference that we see in the mean of one sample and the mean of the other is large enough for us to say that the treatment is different, that the treatment worked, that the drug worked, that this is a better way to produce tires, that this is a better way to produce televisions or whatever product we're working on. And what we want to know is whether the difference that we see is greater than can be explained by sampling error. You are getting data from one sample. You're getting data from the subjects or material in another sample. You compute means for each sample, just as we've learned how to do. You compute sums of squares, or standard deviations or variances for each sample. So when you're doing this type of problem, the problem will be giving you the mean for one sample, the mean from the other, the variance of one sample, the variance for the other, the sample size in one sample, the sample size in the other sample, and keep track of those bits of data. It'll make it easier to solve the problem. And the hypothesis test follows the same four-step procedure that you learned in chapters 8 and 9. When we did hypothesis tests with one sample, we stated hypotheses and we selected an alpha level. We stated both null and alternative hypotheses, and we do the same in the two-sample test. If you have two different ways of teaching, or two different ways of producing something, or two different diets, and you want to know which one is better, if you just feel that one will result in different average scores than the other, we're doing a two-tailed test, and our null hypothesis in that case would be that the mean of the population that went through treatment A or diet A or drug A is equal to the mean of the population that went through treatment or diet B. Our alternative hypothesis would be that the mean of A and the mean of B are different, or does not equal. The mean of A does not equal the mean of B. Another way to write these would be the mean of population A minus the mean of population B equals 0. And our alternative hypothesis would be the mean of population A minus the mean of population B does not equal 0. A could be larger than B, A could be smaller than B, but when you subtract one from the other, you will not get 0. This would be the case of a two-tailed test. If you were doing a one-tailed hypothesis test, let's say if we think that the mean of the population that gets treatment B will be greater than our null hypothesis would be that mean of A is equal to or greater than the population mean of B. And our alternative hypothesis, since we think that B will be greater, would be the mean of A is less than the population mean of B. If you reject this hypothesis, then the only thing you can conclude, if you're rejecting that it's equal to or greater than B, then the only thing that you would conclude would be that it would be less than B. So you remember that your hypothesis have to cover all possible alternatives. We have an alpha level, 0.05, 0.01, 0.10, and if you remember back to chapters 8 and 9, your choice of alpha level depends on how much certainty you want to make. How certain do you want to be that the mean of one group is different from the mean of another? Or how much risk do you want to take of making a type 1 error? If you want to take very little risk, then you would choose a 0.01 alpha level. If you're not worried about making a type 1 error, if you're not worried that you will say there's a difference when there is not, then you might choose 0.10. Similarly, we locate the critical region. If we're doing a two-tailed hypothesis test and our critical regions are in the tails, in either tail. If we're doing a one-tailed hypothesis test, our critical region could either be greater than, or our critical region could be less than. We have degrees of freedom. Only when we're doing a test with two samples, our degrees of freedom are the number of people in sample 1 plus the number of people in sample 2 minus 2. Because we have two groups, we have two parameters that we're estimating, we're going to lose 2 degrees of freedom in each group. We compute the test statistic. In this case, the test statistic, T is the same test statistic, but the formula is a little bit different. We have the mean of group 1 minus the mean of group 2. Now it doesn't matter which mean you call 1 or 2, just keep track of them. And we're going to divide that by the standard error of the mean difference, but because we have two groups, the denominator is a little bit more complicated. You have the variance, the average variance for both groups, divided by the sample size in one group, plus the average variance or the pooled variance divided by the sample size in the second group. And the way you get the pooled variance is you find the degrees, you find the sums of squares for group 1, you add to that the sums of squares for group 2. Sometimes the problems will give you the sums of squares, sometimes you'll have to figure that out for yourself, and you'll be dividing by the degrees of freedom in group 1 plus the degrees of freedom in group 2. Why are you doing this? Well, remember back when we talked about a weighted mean, that if the sample size is the same between two groups, we can just simply add the mean of one group and add the mean of the other and divide by 2. But when the sample size is different, we have to weight the mean depending on the size in the different groups. Well, the same thing happens with a t-test when we're trying to determine what is the denominator. We have to get one denominator. We have two groups, we have two variances. two kinds of variability, two standard deviations, two different sums of squares, and we have to average them. If the groups are the same size, then we could just take the sums of squares for one group, add it to the sums of squares for the other, and divide by 2. But when the group sizes are different, then we have to weight the variances. And we weight the variance, and that's called a pooled variance, S squared P. So what this formula is doing is it's averaging out the variance from one group and with the variance from the other, taking a weighted average, taking the square root of that weighted average, which gives you a standard deviation, and this is called the standard error of the mean difference. And then, depending on the t-value that we get, we make a decision to accept or reject the null hypothesis. The process is the same, the thinking is the same, the logic is the same. We have a difference between two means. We want to know whether this difference is due to sampling error or whether this difference is due to the treatment because we treated one group differently from another. Our numerator is that difference between the two means. We have to divide by, well, what is the typical difference that we expect from two means when we have two groups? But because the group sizes in many cases are different, we have to weight the variances of each group. That's what this complicated looking denominator does. And then when we get this weighted mean, when we get this weighted standard deviation, which is the standard deviation of the mean differences, we divide that into our obtained difference, and then we get a t-value. And this process for getting is a little bit cumbersome. Before you can get S squared P, you have to first average the two variances, and that's what that formula does. If we were to compare the single sample and the two sample hypothesis tests, we have a mean, we have one population mean, we got our standard error by dividing the taking the square root of the variance divided by n, or taking the standard deviation of the square root of n. Both of those symbols are equivalent. We computed our sample variance by taking the sums of squares and dividing it by n minus 1. You learned how to do that in Chapter 4. That gave us our variance. We'll bring that variance over here, and we take the square root of that variance divided by n, or we take the square root of the variance and use this formula for the standard error. They're both equivalent. But when you have two groups, we have two means, we have an observed difference between the means, we are trying to estimate the difference in populations. So our formula, a shortened version of the formula, is mean 1 minus mean 2. And then we're going to divide that. We need some measure of the typical difference between means. And that's what this is. But in order to get the pooled variance, S squared P, we first have to add the sums of squares for one group to the sums of squares for the other and divide by the combined degrees of freedom. Here's your S squared P. We substitute the S squared P into this formula, and that gives us the standard error of the mean differences, which gives us our t-value. And if that's large enough, we reject the null hypothesis. If it isn't large enough, it doesn't pass the critical value, we do not reject the null hypothesis.